Linear programming problems. In earlier classes, we have discussed the systems of linear equations and their applications in day-to-day problems. In this chapter, we shall apply the system of linear inequalities or equations to solve some real-life problems of the types as given below. LPP. The expanded form of LPP is linear programming problems. Optimal value. In profit-related questions, your objective is to find maximum profit, and in cost-related questions, your objective is to find minimum cost. The maximum profit or minimum cost are the optimal values, and the equations of profit or cost in terms of x and y is known as objective function. Constraints. Set of linear inequalities involved in the problem is known as constraints. Decision variables. Non-negative variables x and y. Feasible region. Feasible region is the solution region, or we can say common shaded region from the graph. Feasible solution. The points within and on the boundary of the feasible solutions. Optimal solution. Any point in the feasible region that gives the maximum or minimum value of the objective function. In this chapter, we shall apply the system of linear inequalities or equations to solve some real-life problems. Problems which seek to maximize the profit or minimize the cost form a general class of problems called optimization problems. A special but a very important class of optimization problems is linear programming problems. A furniture dealer deals in only two items, tables and chairs. He has rupees 50,000 to invest and has a storage space of at most 60 pieces. A table cost rupees 2,500 and a chair cost rupees 500. He estimates that from the sale of one table, he can make a profit of rupees 250, and that from the sale of one chair, a profit of rupees 75. He wants to know how many tables and chairs he should buy from the available money so as to maximize his total profit, assuming that he can sell all the items which he buys. In this question, our objective is to make the profit maximum within the given constraints. Let x be the number of tables and y be the number of chairs. Since x and y are numbers, x will be greater than or equal to 0 and y is greater than or equal to 0. The merchant can invest maximum rupees 50,000 and one table cost rupees 2,500 and chair cost rupees 500. Therefore, we can form the constraint 2,500x plus 500y is less than or equal to 50,000, which we can reduce to 5x plus y less than or equal to 100. Also, he has a storage of maximum 60 pieces. Therefore, the constraint is x plus y is less than or equal to 60. Next, we are forming our objective function. In this question, The objective function is a profit function. Profit from one table is rupees 250 and from one chair is rupees 75. Let Z be the profit. Hence, Z is equal to 250x plus 75y. In class 11, we have learned how to graph a system of linear inequalities involving two variables x and y, and to find its solution graphically. We will now solve this problem graphically. Let us graph the constraints stated as linear inequalities. After drawing the straight lines for the equations 5x plus y equal to 100 and x plus y equal to 60, mark the feasible half planes and then shade the common feasible region. In this problem, the region OABC is the feasible region for the problem. Then mark the corner points O00, that is the origin, and A 20, 0, B 10, 50 and C 0, 50. These four corner points or the vertices of that quadrilateral is known as the corner points of this feasible region. Let us now compute the values of profit Z at the points O, A, B and C using the following table. This table consists of two columns. First one for corner points and the second column for the profit Z. Substitute the coordinates of O, A, B and C in the equation Z is equal to 250x plus 75y. Now from the table we can conclude rupees 6,250 is the maximum profit. Hence, he has to buy 10 tables and 50 chairs to make the profit maximum rupees 6,250. Now, read the second question. One kind of cake requires 200 gram flour and 25 gram of fat, and another kind of cake requires 100 gram of flour and 50 gram of fat. Find the maximum number of cakes which can be made from 5 kilogram of flour and 1 kilogram of fat, assuming that there is no shortage of the other ingredients used in making the cakes. Let us analyze the question. Let there be X cakes of first kind and Y cakes of second kind. First type cake requires 200 gram flour and second type cake requires 100 gram flour. But the availability is 5 kilogram flour, that is 5000 gram. First type cake requires 25 gram fat and the second type requires 50 gram fat. The availability of fat is 1 kilogram, that is 1000 gram. In this problem, the objective function is also a maximum function, which is the number of cakes should be maximum. Here Z is the number of cakes. Then the objective function is z is equal to x plus y. The constraints, the first constraint is constraint from the floor. 200x plus 100y is less than or equal to 5000, which we can reduce to 2x plus y less than or equal to 50. The second constraint is constraint from fat, which is 25x plus 50y is less than or equal to 1000, which we can reduce to x plus 2y less than or equal to 40. Here x and y are the number of cakes. It will be greater than or equal to 0. These are the non-negative constraints. We will now solve this problem graphically. Let us graph the constraints stated as linear inequalities. Same like the previous question, we will draw the straight lines for the equations 2x plus y is equal to 50 and x plus 2y equal to 40. Then mark the feasible half planes and then shade the common feasible region. Now look at the common shaded region. It's a quadrilateral, or we can say a bounded closed region with the corner points O00, A20, B2010 and C020. Let us now compute the values of the number z, which is equal to x plus y, at the point O00, A25, B2010 and C020. Now from the table we can see 30 is the maximum value. Thus we can conclude the maximum number of cakes that can be made are 30. That is 20 of one kind and 10 of the other kind. I will continue in the next week. If you have any concern, please comment. Thank you.